matter, which is properties of fluids, in which we will start with the discussion of, non-ideal fluids. And in that, we'll start with the discussion of surface tension and also viscosity. So this is also a very simple, like more or less formula-based type of portion. So let's begin. So surface tension. Surface tension is to do with the elastic property of the surface of a liquid. So first of all, we should properly define what we mean by the term surface of a liquid. Obviously, there's an everyday meaning of the term surface, but in physics, the definition of the surface is a slightly more technical thing. Okay, so a surface of a liquid is defined as a thin layer of liquid molecules that separates the body or volume of the liquid from its environment. Okay, so imagine some liquid in a cylindrical vessel. Any standard liquid like water or kerosene oil or even mercury for that matter, liquid metal. This is a liquid, and this here, this is the surface of the liquid, because it separates the body of the liquid from the, so it's the same, same chemical composition as the body of the liquid, same set of molecules, but it's a layer of molecules that acts like an interface, okay, between the environment outside, like in this case it would be atmospheric air, and the body of the liquid inside. Okay, so the thickness of the liquid, the thickness of the surface, by when we say that it's a thin layer, we should specify how thin. Okay, so the thickness of a surface is taken to be of the order of few times the molecular diameter is extremely thin, as you can see. Now, the elasticity of its surface which is defined as its surface tension is due to the interaction between surface molecules So this interaction is called the cohesive forces. That is the intermolecular attraction forces between the liquid-liquid molecules. So evidence of this elasticity comes from various things that we see in everyday life. We can see that certain insects literally walk on water surfaces without submerging any part of the body. So the surface is able to support their weight like an elastic membrane, like a thin rubber sheet or something like that. Another example which shows the evidence of the elasticity is the propagation of transverse waves. On liquid surfaces. So that would not be possible if it did not have some elasticity and tension. So just give you a minute to go through this section. Yeah, Ritika, a few times the molecular diameter. Okay, so now let's come to the definition of surface tension. Yes, Varun, we have just started, so okay, I'm waiting. Okay, so done with this. So now having understood the basic idea of surface tension, let's come to the definition of surface tension as a physical quantity. Okay. So generally we denote it with the symbol capital T. So as we have already seen in the previous section, this is defined as this is a physical property of a liquid associated with the elasticity of its surface okay, defined as the tangential force per unit length acting at its surface. So let's understand this in more detail first. So if we compare the situation of the molecules of a liquid at a surface as opposed to the molecules of a liquid inside the body, we see how different the intermolecular cohesive forces are acting. So if you consider a molecule inside, then the intermolecular cohesive forces that are acting from all the molecules around it are equally distributed in all directions. Whereas if you consider a molecule at the surface, there are only intermolecular cohesive forces acting in half the volume around it. In the upper part, there's no cohesive forces. So what this does is this creates a sort of a dip in the surface little bit because of this. So the surface is actually little bit bent like this always. And that causes a stretching out of the elastic nature of it, which creates tangential force. Okay. So this nature over here, this is the cohesive forces at a surface, whereas this as opposed to that is cohesive forces inside the volume of a liquid. So this creates elasticity at the surface, and that creates tangential force. So now if we take the top view of the surface, what we'll imagine is that if you think of any line of liquid molecules like this, I had got disconnected, so let's continue. Yeah, so we were talking about the definition of surface tension. So we saw that surface tension is a physical property of a liquid which is associated with the elasticity of its surface. And it is defined as the tangential force per unit length acting on its surface. Now, where does this tangential force come from? So to understand that, you compare the nature of cohesive forces acting on molecules at a surface as opposed to the cohesive forces acting on molecules which are inside the body of the liquid or inside the volume. And you see that because at the surface, cohesive forces are only acting from one side of its surrounding, not from all sides equally. Okay. So they are acting only in half space. So that creates a sort of a stretching out of the surface as opposed to the molecules inside its volume. And that creates this tangential force per unit length. So now you imagine a line of molecules on the surface. So this red colored line, it's an imaginary line of molecules. Okay. So that will be experiencing tangential force like this from both the sides. Is actually, just imagine the surface to be like a elastic material, a thin membrane of that stretched out at the surface. So like such an elastic material stretched out at the surface, like a thin rubber membrane, it experiences tangential force because of being stretched out and its internal elasticity. The same kind of thing happens over here. So this force per unit length acting at the surface, okay, this force is the force due to surface tension. So we define the surface tension as the mechanical property or the physical property of this liquid as tangential force per unit length. Okay. So surface tension is measured in newtons per meter, or a more common unit of it is millinewtons per meter. So this is one way to define surface tension as a physical property of a given fluid. Okay, there is another way to associate it also. We'll talk about that. That has to do with energy, but this is the definition to do with force. Excuse me. So for example, the surface tension of water surface tension also varies with temperature. So at 20 degrees C, for example, surface tension has, water has a value of surface tension which is about 73 millinewton per meter. At that same temperature, benzene has surface tension equal to about 29 millinewtons per meter. Mercury has surface tension of about pretty high, 485, 486. Okay, so next let's understand an example to see how this is incorporated into calculation. So imagine we have this situation now that, in fact, this is like an experiment that you can do yourself also to verify the property of surface tension. Take some fluid which has a slightly higher surface tension than water. Like if you mix some detergent in water, some kind of soap solution, it increases the surface tension of the solution considerably. So suppose we have soap solution in a container like this. Okay. Now you can do this experiment and verify it that if you take a thin metallic needle, which would otherwise sink in the liquid because the density of the metal is obviously a lot more than the density of soap solution. Okay. But if you place it very gently at the surface, you might be able to balance it because of the elasticity of the surface. It's like a thin membrane. So it will, if you place it gently enough, and the liquid has enough surface tension because you mix soap with water in it. Okay. It will be able to balance the weight of that thin metallic needle. So at equilibrium, balanced on the surface, okay, by the surface tension forces. That is tangential forces due to the surface tension. Now you might ask that if the surface is applying tangential forces, how will that balance the weight of the needle? Okay. So the idea is that if you think about it very carefully, you'll realize that at the surface where the needle is present, if we draw sort of magnified diagram, you'll see that the surface is a little bit distorted in shape. It gets a little bit bent because of the weight of that needle. So what happens is that the surface of the liquid gets like a little bit bumped down because of becomes a little contorted like this. Due to the weight of the liquid, the surface is slightly depressed. So if we draw a magnified diagram of the cross section of the needle, what we'll observe is at the surface where it is present, it has caused the surface to get bent or distort like this. So what is happening is that forces that are acting on it because of surface tension are actually acting like this on either side. So these are the tangential forces which are acting symmetrically on either side because of the surface tension. And that is what is able to balance its weight. So these two angles are theta and L is the length of the rod, I mean the length of the needle. Then from this free body diagram, you can see that mg is balanced by, okay, because these forces are acting like this. Where this tangential force is surface tension of the liquid into the length of the needle. So for example, suppose the surface tension of the liquid is 250 millinewtons per meter. The length of the needle is, let's say, 5 centimeters, and theta is, let's say, 30 degrees. Okay. Then we can calculate the mass of the needle from this. Okay, so this is what I am getting as the mass, the needle from this calculation. You can just verify it. So this is an example problem which not just is about numerical practice, but it also gives you an idea about how a surface can apply elastic forces on a material because it has that property of being elastic itself. It acts like a thin membrane which has elasticity, okay, which has the ability to stretch and apply elastic force as a result of that. So that is one way of associating the property of surface tension, that the surface is capable of applying tangential force along it. And that tangential force per unit length is a material property of the liquid involved. So different liquids will have different amount of force per unit length. That is surface tension. So just go through this example and note this down carefully. We'll discuss further. Okay, people, so hope this example is fully clear. Now we come to the next property associated with a liquid surface, and that is the elastic potential energy stored in a surface. So wherever there is internal conservative force, okay, system has potential energy. So for example, in elasticity, we had seen earlier that half of stress into strain is potential energy density or energy per unit volume. So similarly, you just visualize the surface as an elastic material here. So because it's stretched out like that, it's storing some amount of potential energy. So let's understand that. So in this case, it is just called the surface energy. Okay, surface energy of a liquid surface, what it is the elastic potential energy stored in a liquid surface. So now that also depends on the material property of surface tension, okay, and on the size of the surface, of course. So we can just denote it with a symbol like this, capital U surface. So this surface energy, it is the work done by an external agent okay, in creating the surface. So what happens is that liquid molecules, because of their cohesivity, they want to stick to each other. They don't want to stretch out in the shape of a membrane. Okay, that is why in natural condition, liquid always coagulates into droplets. Okay, so as to minimize the surface area, they don't want to stretch out into a large surface. So in order to create a large surface, we have to do, as an external agent, we have to do work against the cohesive forces or the internal forces of the system. So this work done is against against the internal conservative forces, which in this case are the cohesive forces between the liquid molecules. So that work done gets stored in the system as the surface energy. So the best way to derive the formula for this now is to imagine that you're creating a large of liquid which has surface tension equal to T, okay, from nothing, that is negligible surface area. So to begin with, I have the liquid in such a shape that it has negligible surface area, and from that I'm creating a large surface. So in the process, the work done by the external agent will be equal to the energy stored in the surface. Okay. So let's understand how this works. The simple way to visualize an experiment to do this would be, imagine you have something like two thin glass rods which are kept almost in contact, very close to each other. So roughly the same size, two thin glass rods. Very close to each other, you place them. And now you put some droplets of liquid in between them. And preferably this can be a liquid like soap solution again, which has high amount of cohesive force as well as adhesive force between the droplets and the glass. Okay. So this is a liquid droplets. Example, soap solution. Now what we do is, keeping rod 1 stationary, rod 2 is gently pulled outwards. So next what we do is keep rod 1 at rest. And gently pull away rod 2. So now my situation looks like this. You will create a thin film of soap solution liquid, like a thin sheet. Okay, so if you displace this through S, you will see that you have displaced it such that your external force, always having to do work against these tangential forces because of surface tension. Moving this very slowly, so its acceleration is tending to 0. So the length of these glass rods is L each. See that now you have a thin film of liquid with total surface area 2 times S into L. Okay. Because, you know, 3-dimensionally, it's a sheet of liquid whose thickness we cannot ignore. So it's got 2 surfaces. The glass rods being present on either side like this. It's got an upper surface. It's got a lower surface. And this is the film of liquid. The film of liquid will have a thickness typically of at least a few microns, okay, or maybe like, you know, hundreds of microns, something like that. Whereas the surface is extremely thin. Its thickness is of the order of magnitude of the molecular diameter. So its thickness is more of the order of something like, you know, like a fraction, like 1/100th of a micron or something like that. So we cannot ignore the thickness of the film compared to the surface. The surface is much thinner. So it's like this sheet or this film of liquid is bounded by 2 surfaces, one on top and one below. Okay, so the total surface area is 2 times S into L. Now the total surface tensional force acting on the rod, the net surface tension force, that will therefore become 2 times, because there are 2 surfaces, into surface tension into length. Because remember, surface tension is tangential force per unit length. So since my acceleration of the rod is 0, so external force will have to balance this net surface tensional force. So it is 2 times TL. So work done by the external force, which in general is integration F ds. Here it will just become, because it's a constant force. Okay. So that work done is equal to the surface energy, which you can also see is surface tension multiplied by total surface area. So surface energy equals to surface tension multiplied by total surface area. Now the reason why the external force is equal to 2 times T into L is again because there are two surfaces, one on top and one below. So there are force vectors that are acting from both the surfaces. So if you take a magnified side view of this rod, it is in contact with two surfaces, no? One above and one below. So both the surfaces are applying forces like this. Okay. So the net surface tensional force is 2 times T into L. And that is being balanced by the external force as you're moving this very slowly. So yeah, what's more important is the final formula of surface energy. It is surface tension multiplied by surface area. So just go through this once. Okay, Rahul, you want to see the slide earlier? This part, Rahul? Okay, done. Okay, let's move on now. Before we move to applications of this, let's understand the significance of this result that we have here. So this gives us an alternate definition of surface tension. Surface tension T of a fluid is also equal to the surface energy per unit area. Okay, so this becomes important. So surface tension, which we have earlier defined in terms of tangential force per unit length, it's also equal to surface energy per unit surface area. And also, because the total surface energy is equal to surface tension into surface area, so the energy is directly proportional to surface area. Hence, any body of liquid naturally tries to achieve a shape so as to minimize its surface area, and hence surface energy. For stability, remember that minimum energy corresponds to maximum stability, a concept that you know from work energy. The stable equilibrium condition is at the minimum of potential energy. So from that we understand this. Okay. So again, this is evident in what we see as properties or everyday phenomena related with fluids. So for example, droplets of liquid, when in contact, always coagulate to form a larger drop. Coagulate, or you can say coalesce, that is combined. So they naturally stick together. To form a single large drop. So this process minimizes the surface area. And hence surface energy. Another example of this in everyday life is that in gravity-free space, so that can be in outer space or it can be inside a space station orbiting the Earth, where centrifugal force balances gravitational force. So there is artificial zero gravity. A volume of fluid will always take a natural spherical shape. because the sphere has the minimum surface area to volume ratio. Okay, so just make a note of this property also. Surface tension, variability of distance in what sense, beta? Because surface tension is a property that is acting within the fluid, no? From molecule to molecule. Okay, so yeah, it is dependent on the amount of surface tension acting, that is the force per unit length, will depend on the intermolecular distance, which is a physical property of that particular liquid also. No? It depends on the density of the liquid, the shape of the molecules, the nature of the molecules, the kind of intermolecular bonds, whether there are hydrogen bonds present, whether they are polar molecules, all these factors. You understanding the point, Varun? Okay, so let's look at a numerical problem based on this concept now. So this is a very common type of numerical problem at NEET level. Okay. So we have this situation. We have a spherical drop of liquid of surface tension T and radius R. Of surface tension equal to, let us say, 50 millinewtons per meter, and radius equal to, let us say, 5 millimeters. Now, this has to be split into 1000 smaller identical spherical droplets. So find the energy or work done, the energy expended to do this. That is, whatever external agent will have to do, or how much energy they will have to expend. Okay. So the hint to you here is that the energy goes because as you split this droplet into smaller droplets, you are increasing the surface area of the liquid. So you're increasing the surface energy. So you have to supply extra energy. That is why this is a process that won't happen naturally, because the system is losing stability. The reverse of that would happen naturally. If those 1,000 smaller droplets came in contact or very close to each other even, they would coagulate or coalesce into a single drop, because that would reduce the surface area. So now to go in the reverse of the natural process, energy has to be expended. It has to be supplied. So that you have to calculate over here. So just try this question out, people will discuss. So this is one of the most common type of questions from surface tension in NEET or NEET exam. Okay, so people, the first thing you have to understand here is that when you split the droplet into 1,000 smaller droplets, what is the radius of each of those that you get? Okay, so conservation of volume. So let's say each of these smaller identical droplets have radius this much. Okay, so 4 by 3 pi r cube has to be equal to 1,000 times these one's volume. Okay, so this is total volume remains conserved. From this we get the result that r cube is equal to capital R cube by 1,000, which means that R is equal to R by 10. So now in the final state, the total surface area say A2 is 1,000 times 4 pi r square. This is the total surface area. Whereas initially, the total surface area was 4 pi r square. So from this now we can understand that the final surface energy, surface tension into final total area, whereas initial surface energy
So the surface tension in both cases will remain same.
yeah, it's the same fluid, no? So the material property is not changing, right?
Okay, sir.
So work done by the external agent is change in surface energy. So this time you'll see it will become 9 into T into 4 pi r square. So this value will be in joules because I have reduced everything to SI unit. So this little additional part to the problem where we have to do the volume conservation to understand what is the new radius for the smaller droplets, and from that only we can calculate how much the surface energy is increasing by. It's increasing by a factor of 10. It becomes 10 times the initial surface energy. So the change is equal to 9 times the initial surface energy. Okay, so hope this is clear. Now we move on to another property associated with surface tension, and that is the excess pressure that exists inside a spherical drop. So once again, if we imagine a solid sphere shaped drop of liquid of radius r. So again, what you'll realize is that the surface is like a slightly stretched out kind of elastic membrane, because the pressure of the liquid inside is more than the atmospheric pressure or the environmental pressure outside. So this P is equal to P naught plus delta P. So this delta P is the excess pressure inside that spherical drop. Okay. So this is spherical drop of liquid, and that liquid has surface tension T. So this excess pressure is given by the formula. So this drop has radius capital R, and the surface tension of the liquid is equal to capital T. Then the excess pressure is given by the formula 2T by R. Now we'll see the justification of this formula also through a derivation, but much more important is to remember the formula for direct application. So now, to understand how this, and more than that, why this acts, okay, you have to imagine the situation of some part of the surface to understand how the different forces are acting on it, including surface tensional force and force due to pressure. So the simplest way to understand that balance between forces is to make an imaginary diagram of half the surface, that is a hemispherical surface. So think of like a hemispherical membrane of liquid, okay, which is holding the body of liquid inside also, and there is air outside. Okay. So this is like a free body diagram of hemispherical shell shaped surface. So what is happening is that this hemispherical shell shaped surface is experiencing forces like this because of surface tension. Okay, so it's experiencing forces like this because of surface tension. It's experiencing force like this because of internal pressure. The and then it's also experiencing forces like this at the outer surface because of the external pressure. So now if you think of hemisphere, you'll see that the force due to surface tension is equal to surface tension multiplied by the total length of the circumference. So that is T into 2 pi r. The force due to internal pressure, let's write that as F. So this force due to internal pressure will work out to be internal pressure into pi r square. Now we'll discuss the logic of this also, why it's pi r square. and the force due to external pressure, let's think of that as F naught. So that F naught will come out to be P naught into pi r square. From the symmetry of these vectors, you can see that the net force will always be along this axis, this symmetry axis. So the equilibrium of this, that can be explained by the fact that this is how the forces are balancing. And from that, we will get the above derivation. Okay. So just make a note up to this point. Okay, so students, will conclude the lecture here today. I'm having some connectivity issues also. We'll pick it up from this derivation in the next lecture. I think it's day after tomorrow.
Bye, sir. Thank you so much.